Okay, so today we'll be presenting the paper titled "The Motion Excited Sampler, Video Adversarial Attack with Sparked Prior." So we'll do a quick overview of what we'll be presenting. First, we'll present the paper details, and then we'll go through the background for the problem that this paper looks to solve. And then we'll look at the proposed idea, which covers their motion excited sampler, their gradient estimator, and then their adversarial optimization method. And then we'll go through their experiments and their effectiveness, as well as we'll show their experiments on targeted attacks versus untargeted. And then we'll look at their ablation studies, which look at how effective the components of their model is. And then we'll go through the conclusion and give our review of this paper. So the paper details, this paper was just published a year ago, and it has relatively few citations, in part because it was recently published, but also in part because this is a relatively new area, attacking videos. But the authors all are strong authors, strong researchers with good citations. So some background for this problem. So a lot of existing methods treat attacking video the same as attacking separate images. So a lot of the existing methods are white box attacks, and they don't consider temporal relationships. So for example, existing attacks on videos will generate random noise for every frame individually, and then optimize those frames individually before then combining them into an adversarial example. So here they're not actually looking at the relationships between frames for a lot of the existing attacks. So the paper formulates the problem like this, where they are trying to minimize the loss. And I'll pause right there to explain this loss a bit more. This loss is the logits loss, where they're trying to take the maximum of the correct label minus the second rank label. So here, this value, the loss value will get smaller if either the correct label decreases or if the second rank label increases. So going back to this, we are trying to minimize the loss of the model of the sample with respect to the correct label. And then we want to constrain this attack such that the perturbation is less than k. And we want to constrain this perturbation for every single frame individually. And then because this is a black box attack, we want to limit the number of queries. So an overview of the method they propose is they take two video frames and they calculate the motion between these frames. And then they use this motion to map locations in the noise frame that they generate into a sparked prior. So the location of this motion within the sparked prior is given by the noise. And then they combine this sparked prior with the original frames to get their adversarial examples, where they feed that through the gradient estimator, which queries the black box to get an estimated gradient. And then they just do iterative PGD on this estimated gradient. And they repeat this until they get a strong adversarial attack. And the things to note about the proposed method are the black box attack and their gradient estimator, and then their motion excited sampler. So this is what actually incorporates the motion information into this attack. So we'll look at this motion excited sampler a bit more closely. So here they calculate the motion n between two frames, and they take the location in the motion map, and they take the location value and map the random noise at that value onto the location in the motion map. And so that's how they generate the sparked prior. And they generate this motion m. They use two different methods to generate the motion. One is the accumulated motion vector, and then the other way that they use is the optical flow. And now I'll hand it over to Zach to continue.
Okay, so in order to perform this motion excited sampling, we need a way to obtain a sparked our sparked prior from our motion and some random noise vector. So we start with a noise vector sampled from some distribution, and we generate our new sparked prior vector using our motion map. So for a given position, like pixel position, we can obtain a velocity vector, and we set the value of our sparked prior at that given position equal to the noise vector at the velocity vector. So what this does is it ensures that pixels in the same time step with the same motion get the same noise vector. So how we actually calculate the motion vector, this is more of a qualitative overview. It's not so important. You can use other motion calculations. How this is done is they split up the video into n chunks of t frames, where the first frame is an intracoded frame and the intermediate ones are predictive frames. Then you can trace the motion of a pixel to the various p frames and to obtain these displacement vectors. And then because this last frame has all of the motion over this chunk, they just use the last p frame. And this gives us a motion map from the locations in a video to the velocity at that point. This is written as in the paper like so. Here we can see this ith pixel. So if we take this x and y position, we subtract the position traced back. You can imagine projecting this last vector onto this face here, and that gives us our velocity vector. So the formulation for the gradient estimation, instead of trying to directly estimate the gradient, we minimize this new loss function, which is now a function of some guessed gradient. Now, if we think about what this represents, if we think of this surface as being the loss in the space of images, this inner product here is going to be it's going to be minimized when g is in the direction of the gradient of the loss. So minimizing this is we're finding this direction vector. So the big idea is we want to perform gradient descent on the space of image gradients. So we're going to start with some guess for our gradient, and we're going to test how our new loss, like what that value is, by taking a step in the direction of our sparked prior and in the opposite direction of our sparked prior. So start with a guess, estimate the gradient in RS, and then we can update G in the direction of RS. So how that actual calculation goes, the gradient of our new loss in the direction of RS with respect to the gradient estimate. So this is our general formula. And then we're going to approximate it. We're going to find this delta in the direction of RS, which is if we just take the loss of the gradient plus delta RS and gradient minus delta RS. So here's a graphical representation of what this equation represents. We take this point and this point, we find the difference, and that tells us how the gradient changes in the direction RS. Now we can do this substituting our original expression into this equation, and we get this. And the gradient of the loss multiplied by some step is going to be the change in the loss divided by epsilon. Now we can do this substitution for W1 and W2 just to make the equation nicer, and we get this final expression. So how this is done algorithmically, we start with some motion maps sampled from the set of all motion maps, and we concatenate them. Once again, we in this case, they use a normal distribution with mean 0 and standard deviation 1 for each component. So we initialize our random vector. We obtain our sparked prior from this motion map. We get our W1 and W2, calculate our little l, or our new loss for those positions. And then that allows us to estimate this delta. Now, why this sparked prior is helpful is because we use the motion map. If we set our sparked prior to be the same value for pixels with similar velocity, we can reduce the dimensionality of the space of image perturbations that we search. So there's a lot of different ways to perturb in a video. This sort of makes it more direct and more efficient. And with that, I will hand it off to Akash.
Okay, so now we move on to how we attack the videos. So it's a 5-step process. So firstly, we do an initial approximation. So we take the original video and we start with that, and we start the gradient as 0. Then we do an gradient estimation. So we indirectly estimate the gradient as Zach just explained in previous slide. So then okay. So then we do a gradient step. So gradient descent step. Then we combine the gradient descent with the PGD. So it changes the direction of the original direction of the gradient so that it can be turned into an effective adversarial attack. Finally, we constrain the updated video such that it visually looks similar to the original video. So we have two bounds, an upper and a lower bound. Now, so this is the algorithm summarized. So we continue this algorithm till the original label of the video changes. Now coming to the training loss function. So as James discussed, so it's a logist-based loss and instead of a categorical cross entropy. So here this small l denotes the number of classes. Ly denotes the logits with maximum confidence, and Lk is the second most confidence. So here we minimize this loss so as to confuse the model with the second most confident prediction to like make this method effective. Now coming to the framework, they used 4 types of datasets: UCF 101, HMD 51, Kinetics 400, and something V2. So the number of classes varies from 101, 51, 400, and in this dataset it's 175. So the video models they used is Inception 3D architecture and temporal segment network. The 2 types of attacks discussed are untargeted one and targeted one. The perturbation is L infinity. The maximum perturbation is 0.03 for an untargeted one and 0.05 for a targeted one. And then the maximum number of queries, it varies. It's for 60,000 for the untargeted and 200,000 for the targeted. The evaluation metrics are two. First is average number of queries, and the second one is attack success rate. So they firstly tested their model on the pristine video. So firstly, we'll be brief through those two architectures. So the first one is I3D. So it's an inflated version of 2D inception model. The second one is TSN 2D. So it's a long-range temporal structure. So in this, we consider more temporal information via sparse temporal strategy. So we skip some frames in between so that we can take the more information. So now coming to their experiment. So on these 4 datasets, we can see that I3D outperformed TSN 2D in all these datasets. So it's that Inception 3D, it takes into account more spatiotemporal features, whereas TSN 2D, its main focus is on the temporal information. So that's why I3D outperformed TSN 2D in all the cases. So now to check the effectiveness of how their motion spark prior is. So they compared it with 2 different noises that has been previously used in videos. So the first one is multi-noise. So in this we generate a multiple random noise prior, and it's unique for each frame. The second one is one noise prior. So it's same for all the frames. The third one is spark prior that they have proposed. So it's similar to the one noise, but in this we include a motion information. So the smaller the loss, it implies the better the attack is. So these three noises are incorporated in the model, and we can see with the as the iteration increase, the loss value with the sparked prior, the model with the sparked prior, it's generally optimized faster and better than the other two. So now Rahul will take over from here.
Can you hear me?
Yep, we can hear you.
Okay. So we look at the results presented in the paper. So the first row shows the original video frame. It's the clean, pristine video. So the second row shows the motion vector corresponding to this video frame. The brighter regions correspond to the presence of motion in that region in the video. And the third row shows the adversarial video frame. So here we can observe that the adversarial video frame is very much similar to the original video frame. Similarly, they give one more example for one is from the CAP6412 and the other example is from the UCF101. And then they present the main results. The main results include comparison of different untargeted attacks. So the first result is on the dataset something v2. So this research field is relatively new, so they don't have many other literature. So they consider two attacks, ENES, E-bandits. These both attacks are for images. So they try to extend these both attacks for videos. And the third one is VBAD. VBAD is also an adversarial attack technique for videos, but it does not consider the motion information. So ME is the motion excited sampler. So they consider two variants. So one is the optical flow, other is the motion vector. So we see for this particular something v2 dataset, the ANQ, the average number of queries required to fool the network completely is 592. Well, the success rate is 100%. Here I would like to remind you that these are not images. Images we'd like usually consider the L infinity norm. Here it's the success rate and the average number of queries. Since this is a black box attack, the average number of queries required to completely fool the model. And the second data set is the HMDB51. Here also we can see that the proposed ME sampler outperforms other techniques. And the same trend can be seen in CAP6412 and the UCF101. So one thing here we observe is that motion vector usually performs better than the optical flow. This is because motion vectors considers a window of 16 cross 16 to calculate the motion information, whereas optical flow just considers pixelated wise information. And so the second table they present is the comparison of different targeted attacks. So the first one is on the something v2 dataset. So the proposed motion vector algorithm, you can see the number of average queries is much lesser than the VBAD, the second best algorithm. So it's motion vector takes around 20,000 number of queries, while the VBAD requires around 72,000 queries to fool the model. Similarly, for the success ratio, you can see that it reaches 96.6%, while VBAD is 92.95. Similar trends can be seen also for the HMDB51 dataset. So the authors go ahead and perform some ablation studies. So the first question they ask is, do we really need the motion maps? So they try to design an experimental setup that creates a noise-independent motion map. So first one is the multi-noise, where the random noise is sampled for each frame independently. And the second one is one noise, where one random noise is replicated to all frames. So they present the results on CAP6412 and UCF101. You see that the ME sampler requires significantly fewer number of queries while maintaining the success ratio at 100%. So this proves that we really do need the motion information. Well, actually, the motion information helps in creating a better adversarial attack for videos. So the second ablation study is, does the movement pattern in the motion map matter. So now that we have considered the motion map, since it's a video, the motion map keeps changing. So does the movement pattern in the motion map really matter? So they try to handcraft noise with and without the movement pattern in the motion map. So for that, they consider the binary map R, which is the pixel values are 1 when the pixels in the motion map are non-zero. So whenever there's motion, it's 1, else it's 0. So we are still preserving the motion information from the motion map. Then they consider the U sample map, which is, they consider a map U where the pixel values are uniformly sampled from 0, 1 and then scaled and then multiplied with R. Similarly, they consider one more map, which is S value, where the pixel values are ranged in a sequence and multiplied with the binary map. So this experiment preserves the motion map, but tries to alter the movement pattern in the motion map. They present the results on Kinetics 400 and UCF 101 again. We see that the ME sampler, the proposed method, outperforms the other two motion maps. The ANQ is much smaller, while the success rate is 100%. So the authors conclude that the movement pattern in the motion map also helps in creating a better adversarial attack. So the third ablation study they show is how do different losses compare. Oops, sorry. So the present results for Kinetics 400 and UCF 101, the three losses they compare as the standard cross entropy and the probability and the logits. We've already seen that logits has been used previously, and then logits is much better loss function compared to the other losses. And then we see this trend where the average number of queries is less and the success rate is 100% in both the data sets. So overall summary of the paper, the authors say that the attack methods do not directly transfer from image to video. It's not so, very simple for videos. So we need to have some additional information to attack videos, which in this case, they consider the motion information. They claim that this plays a big role in misleading video action recognition models. So the key contribution of this paper is the technique is a black box attack on video models. They try to generate a motion-aware noise prior, which they term it as spark prior. It is effective in both targeted and untargeted settings. So some of the points for the paper is it's a good improvement on existing work. It tries to incorporate motion into the technique. It is modular. It can be usable. It is usable by other video-based techniques. So the results does support their claim that their method is much better. It works in both black box setting and then it works in the black box setting plus targeted and untargeted setting. This is pretty much recently improving field where we don't see much of black box setting attacks on the videos. So they clearly show the gradient derivations, which is a valuable contribution for black box setting. They also give this analysis of the contribution of motion maps. They provide this ablation study to show how important these motion maps are. The paper also has some points against it. The paper shows a large variation in results between data sets. Some results are only shown for a subset of data sets. For the targeted case, they only consider 2 data sets. So it's a new application of existing idea. It's not very novel. It's an incremental improvement. They try to incorporate motion information. It does not spawn many other research directions. So a major drawback is the proposed method still requires thousands of queries. So all the queries are reduced by 50 and in some cases to 90%. It is still difficult to estimate the gradients since it's a black box attack, and then the number of queries range from 3,000 to even 6,000, 7,000 queries in few cases. So it's a lot. That's everything about the paper. We're open for discussion.